I want you to think back to the last time your internet just completely dropped out.
Oh, yeah. Always at the worst possible time.
Right. Just for a split second, but right in the middle of a really crucial moment. Like maybe you were about to hit send on a massive file, or, you're perfectly delivering the punchline to a joke on a video call, and suddenly your face just freezes.
Yeah, in some incredibly awkward expression.
Exactly. And we expect our data to travel instantly, perfectly,
Mhm.
every single time. I mean, it basically feels like magic, but under the hood, routing your internet traffic is, it's a massive, computationally intensive nightmare.
It really is. I mean, the illusion of that seamless connection hides this profoundly complex physical reality, one that is honestly becoming mathematically impossible to manage using our traditional tools.
Which brings us to the core of what we are digging into today. We have a really fascinating stack of notes in front of us for this deep dive. It's covering a cutting-edge research paper that was jointly produced by Comcast Corporation and Classiq Technologies.
Yeah, it's a really incredible piece of research.
And the mission of this deep dive is to explore how the telecommunications industry is actively turning to quantum computing to solve what might be basically the ultimate internet traffic jam. They're trying to balance blistering instant speed with completely unbreakable reliability. So, okay, let's unpack this. Where do we even begin to understand the sheer scale of this routing problem?
Well, first, we have to separate the actual physical cables from the software that directs the traffic. So in modern telecommunications, network engineers look at the infrastructure in different layers. Layer 1 is the physical topology.
So that's the actual, like, glass fiber optic cables.
Right, the cable's buried in the ground or, strung up on poles. It's this vast, really messy web. Then layer 2, the data link layer, handles node-to-node data transfer, which essentially makes sure the hardware can actually talk to each other. But layer 3, that is where the massive headaches really begin.
Because layer 3 is the routing logic.
Exactly. It's the brain. It's determining how a packet of data actually navigates through that physical web.
Yeah.
And to maintain that perfect internet illusion for you, the layer 3 logic has to connect secondary sites, which you can think of as the distribution hubs in your local neighborhood, back to the massive internet backbone terminal hubs.
Right.
But here's the catch. It cannot just find a single path. The network has to find not just one, but two optimal paths from every secondary site to the backbone.
I mean, having a backup route makes total sense. Like a construction worker with a backhoe accidentally severs a fiber optic line, and boom, you need that secondary route ready to take over instantaneously.
Exactly. But this is where network engineers are fighting a two-front war. They have to optimize for speed, so the lowest possible latency, while simultaneously guaranteeing survival through complete redundancy.
And from what I read, that redundancy is remarkably strict. The paper details this requirement for what they call vertex disjoint paths.
Yeah.
So it is not enough to just have two paths that use different physical cables. That would just be an edge disjoint path, right?
Right. Edge disjoint is enough. Because if your primary cable and your backup cable both route through the same intermediate building, which is a vertex on the graph, you have a single point of failure.
Right, because if that specific intermediate building loses power or, a server rack catches fire, both of those cables go dead at the exact same time, which completely defeats the purpose of having a backup.
Completely defeats it. So vertex disjoint means the primary and secondary routes cannot share any intermediate hubs whatsoever. None. They have to be structurally independent from start to finish.
Wow. But the environmental realities make this even more complex, don't they?
Oh, absolutely. The paper focuses heavily on the dual link failure problem. The goal is to minimize latency while protecting against two links failing simultaneously. And we really have to differentiate between independent failures and correlated failures here.
Okay, break that down for me.
Sure. So if the probability of any random cable failing is, say, 10%, the joint probability of two completely unrelated cables failing at the exact same time, like one cable in New York and one in California, is just 0.01. You just multiply the individual probabilities.
Right, that's just incredibly bad luck.
Yeah, but highly correlated failures are entirely different. Imagine two totally different fiber cables belonging to two different vertex disjoint paths, but they happen to be buried in the exact same physical underground trench for, like, a mile.
Oh, I see. So if that trench floods or someone digs it up, both lines are just gone.
Exactly. The correlation is essentially 100%. The joint failure probability isn't 0.01 anymore. It jumps right back up to 0.1.
So it's like mapping your drive to work. You want the fastest route, obviously. But you also need a backup route that doesn't use any of the same bridges or intersections as your first route. But furthermore, if both your primary highway and your backup back road happen to, say, run alongside the same flood-prone river, you don't really have a resilient backup at all.
That is a perfect analogy. And what's fascinating here is how the Comcast and Classiq researchers translated that exact physical dilemma into a mathematical objective function.
Okay.
They created an equation that assigns a massive penalty to what they call cross-path link exposure. The math literally punishes the system for choosing a primary and backup route that share those hidden correlated risks.
Okay, so the objective is clear. But for anyone listening who follows networking, I think the immediate question is, don't we have massive classical supercomputers for this? I mean, why can't we just use time-tested algorithms like Dijkstra's algorithm to just map this out?
That's a really good question. And the answer is that classical algorithms like Dijkstra's are spectacular for standard minimum cost path problems. If you only care about finding the shortest total distance, that's what we call a min-sum problem.
Because you're just summing it up.
Exactly. You just add up the latency of each segment. Say route A takes 5 milliseconds, route B takes 6 milliseconds. The classical computer adds them up and picks the lowest number. Super easy.
But this specific telecom problem fundamentally breaks that additive logic, right?
Yes, because we aren't just adding up milliseconds anymore. We have to balance latency with resilience. And determining resilience involves calculating the joint probability of failures.
Which requires multiplication, not addition.
Exactly. The authors coined a term for this entirely new framework. They call it the min-prod disjoint paths problem. The minimum product.
Being crod.
Got it. Yeah. You are multiplying the risk factors of the two separate paths together to find the overall system vulnerability. And because of that multiplicative objective, combined with those strict vertex disjoint constraints we talked about, they strongly conjecture that this problem is NP-hard.
Okay, and NP-hard basically means as you add more nodes to the network, the number of possible routing combinations just explodes exponentially.
It absolutely explodes.
Yeah.
If you have a realistic regional network with, say, 30 or 40 routing hubs, the number of possible primary and secondary path combinations becomes so massive that a classical computer would literally have to check more states than there are atoms in a grain of sand.
Wow.
Throwing more classical processors at an NP-hard combinatorial explosion just doesn't solve it. The math scales faster than the hardware.
So we basically just hit a computational wall. And I guess that is why the industry is looking at quantum mechanics.
That's the only way forward. But here's the thing. You cannot simply take a piece of classical Python code, hand it to a quantum computer, and expect it to run faster. That's not how it works.
Right, because quantum computers speak an entirely different language.
Right.
We have to translate the physical rules of the telecom network, the latency, the shared trenches, the vertex disjoint requirement, into a language the quantum computer inherently understands.
And that translation process is arguably the most mathematically elegant part of this whole research paper. They use a formulation called QUBO that stands for Quadratic Unconstrained Binary Optimization.
Okay, let's break that acronym down because understanding QUBO seems to be the key to this whole deep dive. So the binary part makes sense here. The quantum system is basically assigning a 1 or a 0 to every possible path segment.
Right.
It's essentially asking, is this specific fiber cable included in our route, yes or no?
Exactly. Yes or no. Then you have quadratic. This is where we capture that shared risk we were just talking about.
Right.
We aren't just evaluating single cables in isolation anymore. We have to evaluate pairs of cables to find that cross-path link exposure.
Okay, so the quadratic element allows the equation to mathematically link two different binary variables and sort of evaluate their interaction.
We got it.
But the unconstrained part, that is where it gets really interesting to me. Because quantum mechanics doesn't process if-then rules or hard boundaries.
No, it doesn't.
You cannot feed it a strict inequality constraint, like path A must never share a hub with path B.
Yeah.
It doesn't understand that. It calculates by finding the lowest energy state of a system.
Right. So instead of building a mathematical wall to rule out invalid paths, you turn every single physical constraint into a heavy mathematical penalty. Flow conservation, vertex disjointness, latency, correlated failure risk, they're all baked into a single massive equation called a cost Hamiltonian.
Okay, so instead of telling the quantum computer what it can't do, you just make the bad solutions energetically heavy.
Exactly.
It creates this multi-dimensional mathematical landscape, and the quantum state naturally rolls away from the heavy penalties, flowing downhill toward the lowest energy valley, which in this case represents the perfect, resilient network route.
Yes. And to navigate that complex landscape, the researchers utilized something called QAOA. the quantum approximate optimization algorithm.
QAOA. I often think of QAOA as the sort of tag team wrestling match between classical and quantum hardware.
That's actually a great way to put it.
Yeah, because you have the classical computer sitting on the outside holding the objective function, basically holding the rulebook. And it tags in the quantum computer, which initializes in an equal superposition of all possible routing states simultaneously.
Right, but superposition alone doesn't actually find the answer. The magic of QAOA is in how it drives interference. The quantum computer applies alternating layers of operations. First, it applies that cost Hamiltonian we talked about, which shifts the quantum phase of the different states based on their penalty weight.
Okay.
Then it applies a mixer Hamiltonian, which shakes the system up, interfering those phases with each other.
Right. So over multiple layers of this alternating process, the good solutions experience constructive interference. Their probability amplitudes compound and spike. Meanwhile, the bad solutions, the ones that, say, share a risky underground trench, they suffer destructive interference and literally cancel each other out.
Exactly.
And then the quantum system collapses into a high probability answer, passes it back to the classical computer to evaluate, and the classical computer adjusts the parameters for the next tag team round to refine the interference pattern.
And if we connect this to the bigger picture, QAOA is brilliant for our current era of near-term quantum technology.
Because we don't have perfect, fault-tolerant quantum computers yet.
Right. If a quantum calculation runs too long on today's hardware, environmental noise just destroys the delicate qubit states. But because QAOA relies on this fast, iterative tag team approach, it keeps the actual quantum circuits relatively short and manageable.
Well, that sounds flawless in theory. The QUBO translation captures the network realities, and QAOA uses quantum interference to find the optimal min-prod path. But theory doesn't route actual internet traffic. Did Comcast and Classiq actually run this on physical hardware?
They did. To prove the model, they designed a specific toy graph network topology. It consisted of 5 vertices, meaning 3 secondary neighborhood sites, and 2 terminal backbone hubs, connected by 7 physical fiber edges.
Okay.
And mapping the structure into a quantum state required 24 binary decision variables, which directly translates to 24 qubits.
And they ran this 24-qubit model through 2 phases, right? First, they used a perfect frictionless simulator. It was a 20-layer Classiq simulator executing almost 2,500 2-qubit gates.
Yes, and on that flawless simulator, the quantum algorithm perfectly matched the exact optimal solutions derived by checking every possible combination using a classical brute force method. So the translation worked beautifully.
But a frictionless simulator is not real life.
No, it's not.
They then took an 8-layer version of this algorithm and ran it on an actual physical quantum computer, the IonQ Forte. And this machine uses trapped ion physics, where electromagnetic fields suspend individual ytterbium atoms in a vacuum, and lasers manipulate their states to execute the quantum gates.
Which is just an incredible piece of engineering. But physical qubits interact with stray magnetic fields, tiny temperature fluctuations, and imperfect laser pulses. Current hardware is inherently noisy.
Which brings up a massive point of friction. The paper notes that a single 2-qubit logic gate on the IonQ Forte has roughly a 99.6% fidelity rate. And on the surface, 99.6% sounds fantastic. But QAOA requires stringing hundreds or thousands of these gates together in a sequence. If I take 0.996 and raise it to the 1,000th power, the math is brutal. You are looking at an overall circuit fidelity of roughly 1.8%.
Yeah. A 1.8% chance of the entire circuit executing without a single error corrupting the state.
Exactly. How on earth can we extract a valid optimal network route from a machine with a 99% failure rate over the length of the calculation? Shouldn't the output just be complete mathematical static?
You would think so. And that is the most remarkable finding in the whole paper. Despite those incredibly low theoretical odds, and despite the mathematical fragility of the noisy gates, the IonQ Forte actually found the absolute optimal, valid routing solution multiple times across their real-world tests.
That's wild. They ran it for up to 2,000 shots or, individual runs. How many times did it actually pull the perfect needle out of the combinatorial haystack?
Well, when utilizing IonQ's specialized debiasing error mitigation techniques, which help suppress some of that systemic hardware noise, the physical machine found the perfect optimal solution up to 16 times out of the 2,000 shots.
Wow. 16 out of 2,000 still sounds really small. But in the context of an NP hard state space, finding the absolute best solution, even a fraction of the time, completely validates the underlying physics.
Exactly. It proves that the energy landscape designed by the QUBO formulation is tilted correctly. The quantum state is naturally rolling toward the optimal valley, despite all the noise trying to push it off course. The signal is distinctly visible through all that static.
Here's where it gets really interesting, though. What happened when they tested the dependent failure scenario? Like when they told the quantum hardware that two separate links were highly correlated to fail?
The shared underground trench.
Yes, the trench scenario.
When they introduced that correlated risk, the algorithm successfully recognized the penalty weight and rerouted the optimal path to actively avoid that shared trench. The quantum computer deliberately chose a route with slightly higher latency, a slower route.
Specifically to guarantee the structural survival of the network. It made that strategic trade-off autonomously.
Exactly. Which proves that quantum hardware can optimize for a multiplicative objective function in a way that classical computers simply cannot scale to achieve. But of course, scaling this up is the final hurdle. A 5-vertex toy model proves the physics, but it's not the internet.
Right. A standard regional network for a telecom provider is significantly larger. You are looking at 30 or more vertices with over 40 edges. To model that for just one routing hub requires 144 decision variables, so 144 qubits, and a quantum circuit requiring roughly 16,000 gates.
And if 1,000 gates drop the fidelity to 1.8%, 16,000 gates on current hardware would definitely result in pure static.
So to successfully execute a 16,000 gate circuit, the individual hardware gates need to achieve a fidelity of roughly 99.98%.
Which feels almost unreachable. But the timeline is moving faster than most people realize. Hardware vendors are projecting they will have 1,000 high-quality algorithmic qubits available by 2028.
That's so soon.
And recent breakthroughs in trapped-ion hardware have already demonstrated that gate fidelities greater than 99.99% are physically possible without even needing specialized ground state cooling.
Wow, so the hardware is literally catching up to the theory as we speak.
Yes. The QUBO and QAOA framework developed in this paper provides a ready, validated pathway. When that high-fidelity hardware comes online, the telecom industry won't have to figure out how to use it. The software architecture will already be waiting. They will be able to instantly leverage it for real-world path optimization at massive scale.
That is just incredible to think about. We are quite literally watching the telecommunications industry lay the mathematical groundwork today for the quantum-powered Internet of tomorrow. So the next time you are on a video call and the connection remains flawlessly stable despite a massive storm outside, you might actually have quantum interference to thank for routing your data around the failure before it even happened.
It really is amazing. But, this raises an important question for you to consider, one that extends far beyond just telecom networks.
Oh.
Yeah. The MinProd QAOA algorithm successfully identified deeply hidden, correlated physical failures in a complex grid. It saw a systemic risk that wasn't obvious just by looking at individual components, and it strategically mitigated that risk. Now, ask yourself, what other complex global networks suffer from hidden, correlated vulnerabilities?
Oh, wow.
How long until these exact same quantum formulations are utilized to map and navigate catastrophic cascading risks in our global financial markets? Or to dynamically reroute global supply chains that are one block canal away from total collapse?
It really puts it in perspective. The telecommunications grid is just the proving ground for managing systemic global risk.